Welcome to Austin, home to the Center for Electromechanics of the University of Texas at Austin, and home to the Pecan Street Project, a City of Austin Smartgrid demonstration initiative. This is the new Miller community in Austin, where said Smartgrid is currently being implemented. The rest of this video will show you how Simulink may serve as the modeling platform for the researchers involved. The power used by homes comes from either of two sources, the utility grid or roof-mounted solar panels. The relationship between these sources and a home's consumption can be described as shown here. The Pecan Street project is currently measuring this field data. Here's an example that shows what these measurements look like for a 24-hour time span. What is currently of interest is the impact that variable solar generation together with home consumption have on the utility grid. Therefore, the immediate simulation focus will be on the utility grid power demand and its direction. As shown here with the blue trace, the grid power can go back and forth between positive and negative. This means that homes are capable of being self-sufficient and of injecting power back into the grid. Referring back to Miller, let's say we have a substation transformer, a cable here, a residential transformer here, one neighborhood here, another one here, and the rest of the system. Let's see how we can model this baseline system using Simulink. This is a simple Simulink model that can be used to simulate a few homes at Miller. The first thing that should be noticed is that the simulation time must be entered in units of seconds. Therefore, to simulate 24 hours, one must enter 86,400 seconds. The reason we choose a phasor type of simulation is because to simulate 24 hours of data, this will only take a few minutes. If we would have chosen a time domain simulation to simulate 24 hours of data, not only would we deplete our computer memory and storage, but it would also take several hours to conduct the simulation. Let's go over each one of the blocks shown here. On the left, we have an ideal source. This ideal source is supposed to represent the output of the substation transformer at a given voltage and frequency. This is a meter that is placed here to measure three-phase voltage, current, and power. The results or the output of this meter will be sent to this scope shown here. This is a cable block. This is taken from the SimPowerSystems library, and it is a three-phase pi section line used as a cable here. The frequency and length can be specified or changed. The rest of the system is modeled as a simple static load where the voltage, the terminal voltage, is specified as well as a desired or intended power consumption. This is a residential transformer. The transformer currently is specified or set to be 50 kVA, but this can be changed at any time. The secondary winding or secondary side voltage is specified or set to 120 volts. The primary to 13.8 kilovolts. These numbers can change at any time. The secondary part of the transformer is center tapped. This means that there's a phase that goes from line 1 to neutral or ground, and a second phase that goes from line 2 also to neutral or ground. The third phase is between line 1 and line 2, and this is 240 volts. This is another meter that is purposely placed downstream of the transformer to see or to observe the transformer throughput. The transformer throughput will be displayed on this scope shown here. These are groups of homes called neighborhoods. Let's look inside neighborhood 1. Neighborhood 1 consists of 5 homes, homes 1 through 5. Each home is modeled as a load profile. The data that drives each home is or comes from this source block shown here. The data that enters this source block comes from the eGauge website. The data from the eGauge website has solar information as well as house consumption information. This data can be exported in intervals of 1 minute. Once the data is exported, it can be made available in MATLAB. Here we show data for houses 1 through 12. The data available in MATLAB enters the house from this source block. It should be noted that the data that drives the house is the power that is seen from the grid looking into the service panel. This accounts for the solar generation at each house as well as the consumption of each house. If energy storage is desired at the residential side of the meter, it can be connected or placed at this point here. This neighborhood shows 5 homes. Neighborhood 2 also shows 5 homes. The data for each house is different. Let's run this model and see what the simulation results look like. After the simulation completes, one can look at the data or the throughput through the transformer. This data shows a 240 volt phasor and 2 120 volt phasors, the currents through the transformer, as well as the power through the transformer. One can also look at the data inside each house, or going into each house. Let's look at this scope, for example. For house 1, we have the 240 volt phasor, 2 120 volt phasor, the current, and the power. Let's look at house 2. House 2 also shows the voltage phasors, the current phasors, and the power consumption as seen from the grid. Having explained how this model works, let's look inside a house and see how that works. If, for instance, we look at house 1 and we understand that the power is driving this house, we must distribute this power into the power consumption in each phase. So step 1 will be power distribution, which means taking that house power and distributing it to each phase. That means distributing the power to the 120 volt loads and to the 240 volt loads. At this time, a random variable is used to create a random distribution. The second part of this model computes the current in each phase as a function of the power profile and the simulation voltage. Once the current for each phase is computed, it is used to drive or to consume power from the grid. 3 current sources are shown here, one for each phase. The currents are computed on the right using the profile power and the simulation voltages. Each house has the same model but is driven with different data. An interesting point is that if one desires to integrate renewable energy or storage at the distribution level, one can use these 3 lines here or here. Additionally, the advantage of using Simulink, or one advantage, is that this Simulink can easily grow. By simply selecting the region of interest, one can simply drag and drag again to make the system grow. Again, drag, and this system is now 6 times larger than it was originally in just a matter of seconds. If one uses the Explorer, one can see the neighborhoods and quickly access the homes. This completes the demonstration video that shows that Simulink may be able to serve as a simulation platform for the simulation requirements at Miller. If you have any questions or any feedback, please email me at the address shown. At this point, Simulink is being used as an experimental simulation platform. It is possible that we may reach the program's limits in the near future, and for this we ask that you as researchers assist in making this simulation as complex as possible in hopes that we may reach or understand what the limitations of Simulink are. Thank you very much.